Thanks very much for having me here. It's really fun to be at Johns Hopkins. I've actually been here very rarely over the last few decades, but I actually lived like on St. Paul Street, the corner of 32nd Street, like for a year, like back in the mid-'80s, 85 and 86. My wife and I got married here. I worked at the Space Telescope Science Institute, so I'd like walk across campus every day. So this is kind of like, I don't know, old home day for me or something like that. Very nostalgic. So Kevin said this is informal. Feel free to ask questions, get up and circulate and get more pizza, and if you want to ask a question, just let me know. But don't speak with your mouth full, please. That was a joke. Okay. So let me start out by asking a big question, which is, what is intelligence? So there are a lot of different aspects of intelligence. So, as intelligent creatures, we sense the world around us. And I'm kind of here including language as a kind of sensing. It's a way of communication and sensing what other people's, thoughts and feelings are. We do learning. We learn from experience. We also learn a lot from instruction. So we read books and papers and extract information from those. We do reasoning, so we draw conclusions from things we already know. We act in the world. I'm not going to talk about that very much. That's kind of like outside my area. So in reasoning, we know a lot about reasoning using declaratively written knowledge in the form of facts and rules. Okay, so they're very mature solutions for reasoning. So there's a whole area of knowledge representation. Essentially what's happened is over the last, 50 years, all the types of reasoning you can do efficiently and effectively have been moved into database or database-like systems. And the ones that we can't do, we sort of still leave as AI. But we know a lot about how to do reasoning. So lately we've been doing a lot of stuff about learning. So learning has turned out to be the best way of solving a number of tasks, including many of the tasks that involve perception. Okay, so learning is something that's become very, very important. Learning from experience has become something that's very important in AI. And even more recently, neural methods have become sort of the dominant approach for most of these tasks, except perhaps for reasoning. So we don't really know how to take declarative knowledge written as facts and rules and integrate it with a neural model. And the problem is, what you end up with here is you end up with knowledge that's very implicit. It's soft, and it's encoded in the parameters of a system and the architecture of a system. It's hard to put your finger on exactly what a neural network knows and when it's used that knowledge. Whereas, here you have some sort of hard, explicit knowledge. So it's not obvious how to put these things together. Although this is not sort of something that's hot, it's just not something that's discussed a lot in sort of like the popular press or something where the enrollment of conferences is surging and they sell out in a few minutes. It's still a case that a lot of systems are built using these symbolic methods, so using knowledge graphs and knowledge bases and databases. So this is really something that is kind of important to understand. So how do we bridge that divide? So people have been asking this question for a long time. So one paper that came to my mind when I started thinking about this, the first one that I read was the system called Knowledge-Based Artificial Neural Networks, KBAN, from 1990. And there the basic idea was very simple. You take a logical theory, like this one right here. You can see how old this is because this is obviously like from some sort of PostScript interpreter from generations ago. You take some propositional theory, you compile it into a neural network. So you construct a neural network that will basically do the inferences in that theory, and then you train it on data to fine-tune it. Okay, and people have been looking at this approach really ever since then. again, a recent paper that I happened to kind of think about because it talked about a bunch of language tasks. So Hu et al., Eric Zing, and Ed Hovey were involved in this paper as well. And the architecture is a little bit more complicated, but the key idea is the same. We're going to start with our logical theory. We're going to turn it into a network that executes that theory, and then we're going to use that network rather than sort of like just sort of simply take that as a starting point that's pre-trained to do that, and then fine-tune it. They had a slightly more complex architecture, but there's still this key step of taking the logic and turning it into a network. All right, so this is the natural way of doing it, the question is, what kind of logics can you compile into a network efficiently, right? And of course, the other question is, once you've compiled into the network, how do you do learning, okay? Is it easy to sort of slap on some sort of loss function and train it and optimize to reduce that loss? So it's an interesting question, because if we look at anything beyond a very simple logic, doing inference, doing reasoning, often requires doing some search. So it's not obvious how you perform search in a neural network. So this is the question that I've been kind of thinking about for a while. And just to kind of, again, be nostalgic and let you know kind of where I'm coming from. So in the 1990s, there was a similar enterprise where people went and they looked at various first-order logics and asked not whether you could compile it into a neural network, but asked whether you could learn it in formal models like Valiant's model of pack learnability. Right? So there's a bunch of formal results which basically say, well, yeah, you can learn this logic under these restrictions, but not under these restrictions. Okay, and you can't really get it from this thing, but the restrictions were really quite severe. So like this is basically a language that you only have, I guess, 3 rules. Okay, or I guess it's just 2 rules, and that's already something that's as hard as learning a disjunctive normal form. And there's some other ones that are also quite simple that you can't learn. This is one approach to looking at ways of bridging neural methods and logical methods, symbolic logical methods. There's another approach, which has also been followed a fair bit, especially in the last few years. And there the idea is you take some architectural component that does something like reasoning, or can be trained to do something like reasoning, and then you embed it in the network. So memory networks, key value memory networks would be one example of these things. Recently, I and other people in my group have been looking a lot at a type of network called a graph convolutional network, which was introduced a couple of years back. And there the essential idea is you have a message passing network where you're passing around not messages, but representations. So one thing that's not clear is it's not clear what kind of reasoning these networks can do and what types of reasoning they can't do. I mean, in some sense, it's hard to even articulate that question if this is a component of some larger neural network that maybe has like multiple layers, so it can do a lot of computation on its own. But it's not really clear how these things line up with the things that we've studied before that we recognize as reasoning. This is what I'm here to talk about today. I have to admit, when I agreed to do this talk, I kind of had in mind that I was going to do this talk. I kind of sent out the abstract. Nobody said anything. And I realized, this is really sort of a very language-oriented group. How many people are doing, ACL-type language-oriented things? How many people aren't? Is anyone not? Oh, you can raise... Okay, can you leave the room, sir? No. So really, I actually probably should be doing this other kind of talk. So there's been a lot of work in my group over the last year or two, and using various sorts of background knowledge and doing various types of reasoning with world knowledge And they've mostly been in the second model where you're trying to take a neural network architecture that's relatively familiar and extend it a little bit in order to do something that you identify as reasoning or using prior knowledge. So I could kind of tell a story behind these things, and then you get the talk, which senior people often tend to do. It's like they come to CMU, and it's like there are 10 people working in their group. So they're like sort of 10 conference talks that are kind of stapled together, like 2 minutes each or something like that. So I decided not to do that for some reason. So instead I'm going to talk about one thing, which is basically a differential logic for reasoning that has the property that's very compatible with neural networks. So it's something that you can compile into a neural network. And I'll talk a little bit about that and why it's interesting and talk about some experiments. So that's basically what I want to do for the next, half hour or something like that. So rather than skip around a lot, I'll talk a little bit more about this one thing. Okay. Okay. So here's some key ideas. Okay. So I'm going to start out. So TensorLog is basically a variant of something called a probabilistic deductive database. So if you guys don't know about that, here's an example of one. So what we have here is a set of facts. So in this talk, I'm going to assume the facts are always unary or binary. Right? So you have one or two arguments. So this is basically a knowledge graph. Okay? And every one of these facts has got some, numerical confidence associated with it. And then on top of these facts, we have a bunch of rules. Okay, so these rules, basically, this little colon dash is, you can think of as an arrow pointing to the left, right? So it basically says, for every x and y and w, if, child xw holds and brother wy holds and uncle xy holds. All right, so this is the head and this is the body, and sometimes this thing is called the neck. So this is the basic idea. If we want to have a rule that has a confidence, you can sort of do that in this framework. What you can basically do is you can put a number on a rule, right? And the way you put a number on the rule is you put another fact on this rule, another condition that has to be tested according to this rule, that only holds that fact is something that has a number, and that number basically, that fact is also only used once, right? So it only appears in the theory just one time. So this is equivalent to putting a weight on that rule. So we also so this is basically the idea behind a probabilistic deductive database, and I'm going to talk about a knowledge graph because I'm just talking about unary binary predicates. So the assumptions here are first that the only parameters are the weights for the facts. The other assumption is that the predicates are only one or two arguments. And then the final one is I'm also going to assume that rules don't have any function symbols in them, so they can't even have constants in them. So here you have to get rid of this tired somehow, and there's another transformation you can do to do that. So that's not an important restriction. It's just sort of a syntactic convenience. So this is a logic, and how can you put this in a neural network? If you're going to use the K-band idea, what you want to do is you want to take every database fact, okay, and make that an input, a potential input. And you also want to have every possible inference that the system could make and make that another unit, another neuron, all right? And then connect these things up so the right inference happens. Yes?
This seems like it gives you a different semantics, like the distribution semantics instead of probabilistic semantics.
Yes. I'll come back to that, okay? But yeah, this is not model counting semantics, okay? So this is one possible idea. But the problem with this, if you do this, you end up with a very large neural network. You can do it, but the network becomes really large. So just in this example here, if I think about all the possible inferences, right, that includes basically every inference about uncle that contains two constants from the database. Okay, and we can connect these things so I get the right inferences, but it's going to be a large set of things, okay, because you're essentially constructing a neuron for every pair of database constants. So this is called grounding the rules. So ground basically means there are no variables. And doing this process by of converting a first-order theory to a bunch of ground facts and then using parameter tying to construct a big network basically doesn't scale very well. So even for something like this, where I just have binary relations, the size of the network can be quadratic in the number of constants in the database. So that can get very big very quickly. So if you're Facebook and you have 2 billion entities, then you don't want to look at n squared. Even if you have 1 million entities, n squared is 1 trillion. Okay, and a knowledge base that has 1 million entities is actually a pretty small knowledge base. Okay, so there are a number of other approaches that people might know about. So probabilistic soft logic, Lisa Couture is associated with that. The Markov logic networks that Pedro Domingos did. These also are turned into probabilistic models by grounding them. Not necessarily neural models, but they're turned into probabilistic models by this grounding process. Okay, and in those systems, you actually construct one ground, an object for every ground instance of a rule. So for every instance of this rule uncle, so every combination of 3 variables, you have to construct a constraint. So this is even worse. It's not just quadratic. It's now n to the k, where k is the number of variables in your rules. So this is an approach that is widely used, but it's not very scalable. So I'd like to look at things that we can use in a more scalable sense. So here's the trick I'm using in TensorLog. So it's a trick that's very specific to these binary predicate knowledge graph oriented things. So when I mean reasoning, the only kind of reasoning I'm going to let you do is answering a query of the following sort. So there's some predicate P, there's some query constant A, and you want to find all the Y for which P of AY is true. And of course, in the soft sense, you want to have some sort of weighted set of those answers Y. Okay. So that's the kind of reasoning you're going to do, and the way I'm going to encode that reasoning, okay, is not by doing this explicit grounding step. Instead, I'm going to encode the input A with a vector, okay, and then the function. Then for every possible inference you're going to build, I'll compile out a function, okay, which will return a vector encoding the answers, okay. So all the inference is vector-to-vector computations. I guess a small detail. So you could actually sort of, I'll use the uncle predicate to find the uncles of Bob, or I could use it to find the nephews of somebody. Right? I could run the uncle predicate, from input to output or output to input. So we'll actually end up with 2 different functions for every predicate. So one which is sort of like the query constant. The input is the first argument. One where it's the second argument. But that's just sort of a small kind of detail. So again, the idea is rather than do this grounding, what I'm going to do is I'm going to define 2 functions. Okay, so if I'm going to ask about some particular object, then I'll encode that with just what's called a one-hot vector. So there's just one component that's non-zero that tells you what the member of that singleton set is. And then the output will be some weighted set of things. Okay, so the output here is going to be a vector encoding a weighted set of database instances. So you get something like that, maybe. Okay. So the vectors here are linear in the size of the database instead of quadratic. Okay, which is makes me feel much better. Okay, so that's the basic idea, or the basic goal, right? So how do we do this?
Back up a bit, just for context. So, what kinds of other reasoning are you giving up in framing this way?
Okay, what other kinds of reasoning am I giving up? Well, if I had like 3-way relations, okay, I'd be giving up the ability to say, I don't know, given this time, okay, what pairs of entities, interacted at this time, right? So you can't answer questions where the answer is not a set of things, right? So you can't answer questions where, the answer is, a story about, how triples of things interact, which you could normally in logic.
I mean, there's a transform that makes any constraint program binary, but it blows up the number of entities in the database. Right?
Yeah, it would blow up the number of things in the database, and it's also going to screw up the syntactic restriction that I'm going to introduce in a couple of slides. Okay. Yeah. So here's the idea behind this. So we're going to describe the reasoning process as a factor graph. So I'll just give you a couple of examples. So let's say I want to, I just have this one theory here, okay? So this is one rule that tells me when someone is an uncle. Okay, so I'm going to compile it into a factor graph. Let's not get to the neural network yet, but let's do a factor graph. Okay, so we've got one random variable x, which corresponds to the logic variable x. All right, so x is a multinomial. It's going to encode a distribution over database constants. Same thing for w and y. Okay, and then parent is a factor. Okay, it's going to constrain the bindings of x and w so that the parent relation holds. All right, that's actually really easy to do. Okay, so parents is just a sparse matrix. Okay, which is, it has the weight, appropriate weight whenever the w for each possible index for w, x and w. That tells you what the confidence in that fact is. So if I want to answer a question, let's say I know what x is, then in the factor graph I'll just pass some messages around. So I know that, we've got a one hot vector that encodes Liam, so my confidence in Liam is 1. Then I propagate that through the factor, and that's basically doing a matrix multiplication of the sparse matrix. So that gives me constraints on w, and so on and so forth. Okay. At each point, the messages that get passed around are vectors. So they're constraints on the bindings of these variables. And in this case, the only operations I need to do are matrix multiply. All right. So here's an algorithm, right? We can build this factor graph. We're going to have one random variable for each logical variable. Okay. And I'll run belief propagation. That will give me a weighted count, which you can show will be the weighted count of the number of proofs supporting each answer. Okay. Sorry?
Only if it's acyclic.
Only if it's acyclic, and we'll move back. So let's get back to this a little bit. Okay. So we can push this a little bit further. So let's say I actually have ant is not something in the database, but it's something that's defined. I can get around that by basically sort of taking the factor graph for ant and plugging it in the right place. And if there's let's say I have another rule for ant, which says ant is let's see, your sister's the sister of your parent or the spouse of your uncle, and uncle is again defined again. We could basically do this. We can take these multiple clauses, and we just, since we're counting proofs, we just add up the counts, all right, and sort of plug those back in. And we can sort of recursively plug in another definition for uncle. So we can basically do fixed depth recursion, bounded depth recursion. We do multiple clauses for the same predicate. And this all sort of works okay. So in general, you can run this belief propagation, and you'll end up with the weighted number of proofs supporting a predicate. So in general, if the graph is, say, cyclic, you have to worry about convergence. So the belief propagation phase may not converge. So for TensorLog, I'm making a further assumption. So I'm assuming all the trees are polytrees. So basically it means every free variable has one path of dependencies linking it to a query variable. All right. So then the belief propagation is really easy. It converges in linear time. You just get a fixed sequence of messages. All right. It turns out there are only a few operations that get used in these matrices, in these messages. So matrix vector multiplication, there's component-wise product. There's one other one here, which is really sort of Hadamard product, where you have it's really basically a matrix vector multiplication where you have a dense matrix of all ones, and I guess vector sum and normalization. For this sublanguage of logic, you can basically take your theory, okay, and you can take a particular type of query. So maybe this is like the predicate, status, with the first argument as the input, okay, using R3, and we can just we can run the belief propagation, or we can simulate it, figure out what sequence of messages is constructed, okay, and then we're done. That's basically the kind of function we're trying to construct. So this is a differentiable function which I could sort of easily embed in a neural network. I could, encode it as a bunch of, let's say, TensorFlow operations or a PyTorch model. And this does the inference that the logical theory does. Okay. Yeah. So this is actually this idea of like taking this belief propagation step and unwinding into a neural network. I should say is exactly the same idea that Jason Eisner and Matt Gormley did in his thesis, and it may have been done before then. I'm not sure. But essentially, you're just unrolling that propagation phase and turning it into a network. So Jason asked this question about the semantics. So what's going on here is you're doing a soft count of the number of proofs for each query. So you're trying to find out how many proofs support the query. This is, I guess, people have used this before, so it's independently motivated kind of semantics. So essentially, this is something called a stochastic logic program, or a variant of one. So this has been around for a while. And the thing that's new here relative to the old style SLP is that now there's a dynamic programming algorithm to compute these weights efficiently. And that will work in some cases where there are exponentially many derivations. So that's all good. Now, this is not the semantics that many people find most natural. So one problem with this is that what the numbers mean, and remember these numbers are little numbers that are associated with each fact. Ideally, you'd like those to have some semantics that's independent of the particular syntactic form of the theory that you used. Okay. Semantics that a number of people have proposed in the past is a model counting semantics. So there, essentially, the idea is the rules are just hard rules. And those numbers are used to define a distribution over hard databases. So essentially, the idea is you look at those numbers, you go through every tuple in your database, you flip a biased coin to figure out whether you want to put that tuple in your database or not. So that gives you a distribution over databases. And when you answer a query, the number you want to get is what's the probability that that query is true, given the theory, which is just a hard theory, and this distribution over databases. So you're basically marginalizing over the soft choice of a database. All right. So this is very conceptually simple. The weights are arguably more meaningful. But it turns out inference in these models is very expensive. Even the simplest versions of these things are at least Sharp-P complete. Okay, so this is what I know in terms of complexity. So for TensorLog, the inference is linear in the size of the theory and the depth of recursion and the number of facts in the database. Okay, so that's about as good as it's going to get. All right. If I drop the restriction to a polytree, then in general the inference is Sharp-P hard if you're going to try the proof counts exactly, precisely because we can have cyclic things and we can have like convergence issues. There's obviously a lot of work on doing approximate reasoning in factor graphs. So the fact that it's Sharp-P hard with loops doesn't necessarily mean we should throw up our hands and avoid that area forever. But for now, I've been throwing up my hands and avoiding it. Okay, so that hasn't been done yet. Okay, and the other thing is if I take the same logic and replace the proof counting semantics with the model counting semantics, it's Sharp-P hard. Okay, so in some sense, this is sort of a maximally expressive subset. If I drop any of these restrictions, it gets hard. All right, so now I've kind of told you what I mean. Let's look a little bit at some numbers. First, learning algorithms, okay? So when I first wrote up a draft of this paper and distributed it to some friends of mine that look at probabilistic databases, they said, you didn't really talk about the learning algorithm. How do you do learning in this? It's like, I don't have to talk about the learning algorithm because it compiles to a neural network. right? So all you really do is you now have a numeric function, okay? You define whatever loss function you like. So if you've got like some target set of values, and let's say you want these things to be a distribution, then you can say like cross entropy of the softmax. So you're basically putting kind of like the most common neural network loss function on top of your proof counting output, and then you just minimize the loss with whatever you like, atom or eta grad or whatever. And you can use this to adjust any of the parameters. Now, the only parameters in this system, the only numbers I have, are the numbers in the database. So that's what you're going to tune. So in practice, what you do is I select some parts of the database and say, these are things you want to learn, and some parts of the database and say, I think I know what these numbers are. Maybe they're really all just ones and zeros, okay? So what you're learning to do is adjust weights for selected database relations. So that's what you do. So which one of these should I use? This one, okay. So there's actually two implementations of this. So one thing I've done is looked at compiling this to TensorFlow, okay, and that's kind of the baseline implementation now. The other thing I did is I looked at sort of a homegrown implementation. So TensorFlow runs on GPUs, and it supports sparse matrices and sparse matrix multiplication, but only a little bit. So you can multiply a sparse matrix by a dense vector or a dense matrix, but you can't multiply two sparse matrices in TensorFlow. So so the SciPy lets everything be sparse. But on the other hand, it's kind of like a homebrewed neural network platform. So, that some professor and his students wrote. So what are you going to get out of it? Who knows? So here are some experiments. This really what I had next? Yeah. This is fine. So here's an experiment, and this is really just sort of a illustration of some tasks that you could do with this. Okay. So one thing I'm quite interested in is question answering. Yes, question.
So you mentioned about why there can be multiple answers for a given question because the answer is.
Yeah. Right. Okay, hold on to that. I think I'm going to get to that in a couple of slides. That's a great question.
So I wasn't really clear about the learning. The factors have these sparse matrices, right? So
right.
You're learning the non-zero elements of
You're learning the weights of the non-zero elements of the sparse matrices.
So the zero elements, they're just zero.
The zero elements stay zero. Yeah. I don't want to change the size of the database, essentially, particularly. Okay, so here's a task. The input and output are questions and then answers, and the answers are all taken out of a knowledge graph. Okay, so who acted in the movie Wise Guys? It's this list of actors. Or what's a film written by Luke Brickey? It's this is the only film he wrote. Okay. So we basically have these questions, and we have a small knowledge graph of movie information. And people have looked at this in the past. So the techniques that have access and use the knowledge base sort of get in the mid 90s. So this is like a pretty clean data set. So here's one way of encoding this in TensorLog. Okay, so we write the following theory. So I'm going to answer a question with an entity if the question mentions a movie, okay, and the movie stars some particular set of actors. So those will be the answers. All right, and also I want to say that this is the right kind of relation to use for this question. All right. So to say that, I basically have these additional conditions. So I'm basically saying the features for this question indicate that I should be using the starred actors thing, and I should be using it in this direction with the movie as the input and the entity as the output. Okay, so input, output. Okay. So the weights for this feature that are listed here are basically what I want to learn. So I'm trying to learn which questions go with which movie. So the actual execution of this is all sort of in the same model. So so I don't have to give this any explicit training as to which rule to use where. Instead, I'm just giving it input and output information. So it's a distant training technique. All right, and here's the other case, or an example of the other case. I've got the answer to a question is a movie, and so the question mentioned some other movie entity, like maybe a writer. Okay, and the movie was written by that thing. So now I'm taking that written by thing. I'm using a different relation in a different direction. So I have another weight, all right, associated with that. So again, I've got to learn all these weights to get this work. So I basically have two weights, weight vectors for every relation. And those are basically, if you want to think of them this way, as a classifier that tells you which rule to use to answer which question. Now, could we do like a different type of classifier? Could I take that question and run it through an LSTM and then do a classification based on that? Let's come back to that a little bit. So this basically works. This is the time on one machine with one GPU. And this isn't super fast for a neural network, but it's actually really fast for a probabilistic database. So this is very fast for a probabilistic language. So in my example, I'm basically assuming that mentions entity is known, but we could imagine extending this model. So if I didn't know which entities were mentioned in each question, I wanted to put that in my model. I could imagine doing that. So you could imagine the mentions entity is defined by rules that are based on simpler things like what n-grams are contained, right? And what words are contained in those n-grams. So I haven't done this, but it's clear that this would extend to somewhat more complex types of queries and settings. So here are some other numbers. This is like some standard relational model. So this is using a handwritten rule set. These are using rule sets that were constructed using another kind of relational learning system. And this is comparing to a system I developed a few years back with William Wang, now at UC Santa Barbara. So roughly this is sort of comparable in two of the three domains and better in the third. But the nice thing about this is architecturally this is very different. So proper sort of a standalone system. If I want to integrate it with some neural network stuff, it's hard to see how you do that. So here's some scalability issues. So this is a kind of simple social network reasoning task. So this is kind of a toy social network. The inference you do is actually pretty shallow, just a couple of layers. So we can use a pretty big network. So this is like using 2 million entities. This is much smaller, but we're going to be doing much deeper reasoning. This task for these GR things is reasoning on a grid. So this is something that's been used as a benchmark in sort of the probabilistic logic community. So I've got entities that are names of cells in the on a grid, all right, and the facts are all edges. So the edges all start out with a weight of, I think, some constant number. I think it was 0.2 in these experiments, and your theory is basically a transitive closure, right? So it basically says there's a path from X to Y if there's some sequence of edges that connect it. What you're going to do is you're going to train this so that when you ask for the things that are connected to Y via a path, well, A, it's going to be bounded depth inference. So you're just going to go, say, 10 levels deep. And B, you're going to ask for a particular path. So you're going to send it a signal that says, what I want you to do is always go to the nearest landmark node where the landmark nodes are, say maybe the one's divisible by 10 or something like that. So here's some scalability issues. So just kind of briefly, these are the three different versions. The SciPy implementation, and TensorFlow on a CPU and TensorFlows on a GPU. So there are, I guess, two things to talk about here. So one is, since this is built on a neural network system, we have the possibility of doing some things we couldn't easily do before. So in a neural network, a kind of standard thing is you take a bunch of examples and you put them together in a batch. mini batch. And then those all get done in parallel. So we can do that here, and using parallelization, using a decent sized mini batch is always an improvement. So the faster things are always using a mini batch. Okay. So the GPU is not tremendously faster, which surprised me a little bit, until I started looking at experiments involving learning. So this is doing the learning task on the grid. Okay. So here the old SciPy implementation starts taking kind of more time than I wanted to spend fairly quickly. Okay. The GPU implementation, though, is really fast. So learning is much faster. So these things are, of course, architected for repeated passes over the same data. And they do that really well. I maybe we'll skip this thing in the interest of time and just talk about a couple of extensions to this. So are there questions before I kind of move on? I don't want to. Okay. All right. Somebody said, do you really want to have this y star, right, and a cross entropy constraint? Okay. So this is fine if there's one correct answer, but there could be multiple correct answers, right? So you can have multiple uncles, right? And, if you're just looking at, so there's some things you can do just by kind of like ranking, you could say, well, these are the top two people that might be in an uncle relationship. But ideally, you'd like to know and be able to tell the difference, from the output, whether you've got, with high confidence, two uncles, or, there's one guy that's, uncle, but you're not sure which of two guys it is, right? You'll like to be able to distinguish those things. So you can't do that with a normalized vector. It's great to optimize. It's a lovely function to optimize. Neural networks love optimizing this function, but it may not be what you want. So we can put a different sort of model on top of this, though. So we can essentially stick here. So g of x is the proof counts, all right? And so we can basically say, well, I'm going to basically build a little sigmoid model, a little logistic regression that takes those proof counts and decides whether we're going to threshold them close to 1 or 0. So now you're learning a biased sigmoid. I think there's actually a scaling factor in here in the model I used. So this is an example of two things. One is I'm taking sort of the proof counts and I'm putting a little bit more computation on top of that, which of course you can do because it's just a neural network. It's easy to add a little bit of additional computation. The learning is still free, and this lets you match an arbitrary distribution. So Jason asked a question about model counting systems. So there's systems like probabilistic and others that implement these systems. And like I said, I didn't go there because it's expensive to do computationally. Okay. But let's see how close you can get to that. So the hypothesis I have here is I want to have a semantics that's really fast to do inference on. And then I'm going to learn the values of the parameters. So don't worry so much if you don't know what those parameters mean or how to set them. We're going to learn them anyway, right? Because I don't really believe you know how to put those numerical parameters in there anyway. I'm sorry, I'm a learning person. Parameters are not for people to make up. Machine learning systems should make up parameter values. All right. So what I'm going to do is I'm going to sort of see whether I can train the system to come up with probability estimates that are similar to the estimates of a problog-like model. So to estimate that, I just did a sampling. I just sampled a million random grids the way the model says to do, okay, and use that as my numbers. And here's some numbers. So this is the error rate before and after training. So the error is actually, when it starts out, it's really doing nothing like at all what problog does. When it finishes, it's pretty close. So this is a kind of a SPY plot. So this is showing you at each one of these things, we've got a grid cell here and a grid cell here. This is on a 10 by 10 grid, so a little tiny one. Okay. And this is before training TensorLog. So this is what the probabilities look like. this is what the probabilities look like doing transitive closure computations on the sample. So you can see they're really different. This is after training. You can see they're pretty close. Here's another thing. This is just the error, the relative error, the TensorLog model versus the problog2 sample model. So again, before and after training, you can sort of see it's getting it to some extent. I don't know whether this is a great approximation or not, but it's a proof of concept or something. Another question is, can you take a neural model and stick it underneath? So maybe you don't want to have like a simple linear model for what type of rule to apply to which question. Maybe you want to build a much more sophisticated model, right? So here's a little toy experiment which is doing something of that sort. What I'm going to do is I'm going to take some representation learning. I'm going to stick it underneath the TensorLog model. So instead of just having a number for each edge, I'm going to replace the weight for each edge with a function of learned representation. So I have a single representation for each cell. Let's just make that a two-dimensional number. So I could do the kind of navigational tasks I had if I knew what the x, y coordinates were of each cell. You don't know that, right? But I tried to set this up, in a way it was like, well, let's pick up a task where the x, y coordinates would solve the problem and see whether it can learn that representation. So the model I chose looks something like this. So you basically look at the difference between the two encodings. All right. So this is basically a two-dimensional difference. So it's kind of like Manhattan distance, but it's telling you to go in one direction or another. Because when you're navigating to a landmark, you have to know which direction to go. Okay. And then we're going to take those differences and we'll add them up, and then we're going to run them through this thing right here, which is a soft plus. So we're making it positive. So we have positive edge scores because it seems unnatural to have negative scores in this vaguely probabilistic model. Okay, and then I'm masking it out so that the only things that have grid cells are considered. Okay. So this is my model, and the goal now is to come up with these embeddings for the grid cells. Okay. Why is this? This should be. What is it? Yeah, E1 is the embedding for cell 1, E2 is the embedding for cell 2, and I'm summing over the dimensions of the embedding, I guess. That's what's going on. Okay, so I guess briefly this works. Converges really nicely. Anecdotally, it did not at all recover Euclidean space. I didn't give it a problem that was nearly that constrained, so it came up with something which also reflected distance to a landmark, but wasn't what I expected. So one more quick comment. I'm going to try and end soon, so we have a little bit of time for questions at the end. In this whole discussion, I'm assuming you have inference and you know what the model is, right? You know what the theory is you want to use. An interesting question is, can you learn the theories as well? So there's been a lot of work on this. So we, with the student Fan Yang, we looked at doing this for a slightly restricted version of TensorFlow. So we just have the examples and the outputs, right? We don't have the theory. We'd like to learn the theory, and we're going to do this in a kind of a smooth, differentiable way, right? So the programs, of course, are compiled to a series of differentiable operators. So anything I can do in TensorLog, I can do by applying the right sequence of those operators to the right logical variables. Okay, so I've got a model where I have this set of operators, okay, and I have a memory. Okay, each memory is basically a logical variable. And I want to learn to sequence these operations with a neural controller. Okay, so the model is basically at each step we have a finite state controller. At each step, it uses attention to choose a memory cell. Okay, it uses attention to choose an operator. Okay, and the number of operators is linear, basically, in the number of relations. Then it softly applies that operator to that memory cell. You end up with like sort of a mixture of objects again, and that gets added to the memory as sort of the next logical variable. So that's the basic idea. At the end of the day, you've got a bunch of logical variables. You don't know which one contains the right value. So again, you're going to use the hidden state of the controller to give you attention over the memory cells to figure out what the right answer is. So kind of like briefly, this works okay. So this is on these kind of standard statistical relational learning systems. It actually gives you much nicer results than previous systems. We also tried it on this wiki movies data where essentially it's trying to learn the theory that I wrote. One slight difference here is you're giving it a natural language query, which is just a kind of bag of words encoding. The neural encoder can, of course, have inputs that are not necessarily, memory cell vectors. So it's pretty easy to extend that way, and it's pretty comparable. It's just a hair lower than the handwritten model. All right. So a question which sometimes comes up is, what am I doing next? I've talked to this model to a number of people at Google. They kind of find it interesting, but I think ultimately this is kind of a hard sell at Google. So people don't really, many people don't really understand this kind of declarative programming. If they did, it would still be hard to kind of program this kind of declarative model, this first order logic model, in a setting where you were combining it with TensorFlow models sort of underneath or on top of the logical components, because you'd be swapping back and forth between this declarative style and this functional style. So one thing I've been looking at is designing a language, which is basically a programming language that lets you write down in some sort of relatively meaningful way the things that that TensorLog gets compiled into. So just to give you a little bit of a flavor, this would be what the kind of model that I showed you for the question answering thing would look like. So you're basically starting with a question, and we're sort of following some relations and chaining, okay? And there's also these gating conditions. So this is going to be true if this set here is non-empty, and this set is basically starting with a string starred actors and kind of moving backward through this set of weights. So this is basically the set of words that indicate starred actors, the set of features that indicate starred actors. And then we're looking at and intersecting that with the question features. So it's not too bulky, much more bulky. You really only need sort of a handful of constructs. All right, so just to wrap up, so the question I'm kind of been looking at is how do logic and logic programming approaches to AI stack up, and more particularly, is it worthwhile trying to integrate them with like these deep learning approaches? So I think it's a worthwhile thing to do is to consider this kind of integration. TensorFlow has one answer to this. It's scalable but very restricted. Try to keep things very efficient for learning and inference. And you can, in fact, combine it pretty easily with neural methods, either by sort of putting them underneath the TensorFlow model as computed signals for the predicates or on top. So this is definitely not the only plausible answer. I'm also spending a lot of time working in and looking at other approaches such as graph CNNs and memory nets. So they also can encode some very interesting logical operations, and I think understanding what they do and how it relates to existing logics is another very kind of interesting and important area. So I'm going to stop now, and thank you all for coming and for your attention, and I'll take questions if you want. Yes, right. Well, I mean, you could decide to have a dense matrix instead of a sparse matrix. And I mean, a dense matrix can be represented as a sparse matrix. It's just a little bit of extra overhead. And there are actually a few dense matrices in these experiments. So when I look at the weights between words in a question and the types of operations you're going to apply, the types of predicates you're going to use, then that's a mapping between words and database relation strings, names, and that's dense actually. So you can decide to have things be dense if you want. You don't generally, I think, computationally, you don't want a sparse matrix to change size. So generally, that is an expensive operation to do at the matrix level. You have to do some sort of reallocation, and memory management for that to work. And also, the potential size of these sparse matrices is very large. So those matrices are generally quadratic. The dimension of those matrices as dense matrices would be quadratic in the size of the database, right? So if you have 1 million entities, right, then it would be like 1 million squared non-zeros. You don't want to let your model do that, okay? You don't want to let it get that big. And you don't want to try and put that much memory on a GPU. So I think the right thing to do is to basically sort of fix the size of the set of parameters you're going to use and vary those parameters rather than sort of try and recruit. And again, it's like sort of like computationally, it's like I don't know if I can even think of, back in the 80s and 90s, people talked about recruitment learning where you'd sort of add new non-zeros to a neural model. But nobody does that. The models that run on GPUs don't really support that very well. I think it's probably more expensive than you want.
Just to follow up, I think the other way would be low rank factor, where it's basically 2 ways.
So right, you could do low rank factorization and only implement. Instead of having a sparse matrix, you could have like a factored matrix. Yeah, that would certainly be a reasonable thing to do. So if you did that, you're introducing an error in your database, right? So it would be fine if your confidence in the database was uncertain, and you're happy introducing error. It might be harder otherwise. So, yeah.
So this may be following up on the previous question, but I get a little worried with systems like this that they don't have any ability to memorize facts when those are presented somewhere. So you say who's married to Donald Trump and it says Michelle Obama because the embeddies are similar enough.
Right. Well, I mean, you could have a knowledge graph of like marriages, celebrity marriages, or something like that, right? So that would just be a sparse matrix, and you could say it's not a parameter. You can't change it, right? So in some sense, you can memorize facts, right?
Just do it additively
So to change it, yeah. So right, if I add a fact, then I'm changing the sparsity of the matrix. So there's like some like computational complexity in that. But yeah, you could certainly, conceptually at least, you could do that, right? Yeah. Yeah, Kevin?
So say I just want to improve my NLP system, like a IE system or NP system. What kind of logic?
In your NLP system?
Yeah.
Probably depends on what your NLP system's doing, right? I mean,
Information extraction, but what kind of logic?
so in information extraction, I mean, so we sort of know from like Nilau's work on PRA and all this like knowledge graph completion stuff, we know that a lot of the new values that you see can be predicted or partly predicted. They can be predicted with some confidence, right? You can lower the complexity of new relation elements by looking at existing relations, right? So having some sort of system that will let you softly reason about other things and say, well, I think, in this sort of situation, maybe he is your uncle, right? It's like, it's like, okay, it's like, I don't know that she's your parent, but you have a child, but, she's married to your father, so, maybe her sister, maybe her brother is your uncle, right? So, in actual knowledge, in, realistic knowledge bases, there's lots of sort of potential redundancy of that sort, and you can learn, rules or theory-like structures that will sort of capture some of it. So I think for information extraction, it probably would be useful to have this kind of machinery. And one way it could act is by sort of like lurking around and acting as a prior for what you extract.
Any other questions? If not, let's thank William again.
Okay.